So we are live. Hello, Internet. No one's watching. It's okay. But if you, again, find yourself at home or unable to come to class, you can join us in with us on YouTube. So I'm not going to go through the whole history of science, definition of science. That's not what this class is about. But you do need to know one very important distinction that has to do with scientific definitions and that will inform how we talk about everything else from here on out. So I want to start there. So science is often described in terms of theories and laws. Have you heard of that before? The idea of a scientific theory versus a scientific law, that kind of thing. What do you think that means? Or what's the difference between the two? You don't have to give a specific definition, but how are those different to you? How have you heard them used? What are they?
A theory is something that has, like, people have proven to be pretty true, but maybe not necessarily a law.
Okay, so then how is a law different?
A law really is, I don't know.
Okay, so it really is. So it's sort of like a theory is like a baby law.
Like an idea.
Like an idea. Okay.
That can be maybe proven.
Okay. Of what can be proven? Yeah.
I'm thinking that maybe a theory is something that people, people's theory,
Okay.
but a law has been backed up by math.
Okay.
It's been proven to.
Proven with math?
A law.
Yeah. Okay. What else? Have you heard of these things before? Somebody give me an example of a scientific law. Newton's laws. Yeah. Yeah, that's a good one. Can somebody give me an example of a scientific theory? Theory of evolution, sure. What else? Others? So we'll look at quite a few of them this semester. Atomic theory is a big one, the theory that matter is made up of atoms. These terms are a little bit troubling or troublesome. We run into problems with them. And the reason is, I think, because we have other definitions for those terms outside of science. Like there are laws that are don't have anything to do with science, right? Like rules that you have to follow, those are laws also. We also have theories like this idea that just something you think about could be a theory. I have a theory about that. Or I think somebody said it, right? Like you're theorizing, you're just coming up with some ideas is theorizing. So those are non-scientific definitions of these terms. The problem with that is that the scientific terms their definitions get a little fudged because of our experience with those terms popularly. So I want to be more specific about, in science, what do these things mean and why is that different? Well, you'll see how it's different, but why is that important from the other? So we'll start with the laws. The laws in science, like Newton's laws, is pretty simple, actually. It's a set of observations. So you see something happen a bunch of times, and then you just describe it, right? Every time there are two objects, they will attract each other with a specific force that we call gravity. And that force is proportional to the product of their masses and inversely proportional to the square of the distance between them. I don't know if you've heard that before in physics, but anyway, that's called the law of gravity, because everything we ever observe behaves in that same way. So we call that a law. All right. Another way that I like to think about it is what happens. In a few chapters, we're going to talk about gas laws, laws that apply to gases. There's a law called Boyle's law that says every time you increase the pressure on a gas, the volume goes down, meaning the space it takes up gets smaller. Because every time you do that, it seems to do that, and so we describe it. And that's what we call a scientific law, a set of observations of what's happening. What doesn't that tell us? Or if somebody said to you, hey, here's this thing that I keep seeing happening, what might be the question that you ask that person? Why? Why is that happening? Why do Newton's laws work? Why do laws of thermodynamics work the way they do? Why do, what else did we talk about? Gravity. Why does that work the way it does? So we want to know why, and where do you think that is? That's the theory. So the theory is the explanation, the why. Now let's be more specific here. Notice that neither one of those is better than the other. Neither one is more true than the other. They both require evidence to back them up, and they can both be disproven if there's enough evidence against them. All right? And I think that this comes from the idea of laws as rules, like that a nation makes laws and sets rules. Because what happens in government? Somebody proposes a bill and it gets voted on and negotiated or whatever, and then it becomes a law. So we think like, oh, something starts as something and then it becomes a law when it's good enough. And that's not the case in science. We don't start with a theory and then when it becomes good enough, we call it a law. And that's totally the popular assumption of what theories and laws are, that a theory is like a baby law that doesn't have enough evidence yet. And if it just gets a little more evidence, we'll finally call it a law because it's super true. That's not true. That's not how it works. In science, a theory and a law both have evidence supporting them and can have evidence against them. And these examples that we came up with are some good examples of that. Newton's laws, for example, the laws of motion, projectiles and all that kind of stuff. Are they true? Are they true laws? Kind of. They kind of are. Anybody know where Newton's laws don't work so well?
In space.
In space. That's true. Why?
There's no gravity.
There is gravity in space.
Is there?
I mean, I guess not in like open space, but like planets have gravity with each other in space. But you're right. You're right. And in fact, Newton's laws break down in really, really big things like space, where you're talking about huge bodies and huge distances. And then Newton's laws break down in really, really small things, like in atoms. And that's where we have things, something called quantum theory. Have you heard of quantum mechanics, quantum physics, quantum chemistry? That is a better theory or a better set of ways to describe things and in those particular scenarios. So we don't say Newton's laws are wrong because they totally work fine at our normal scales that we're used to. Like if you shoot a projectile, you can calculate where it's going to land based on Newton's laws, and that's fine. But if you have an electron that's moving through an atom, you can't use Newton's laws to calculate how it's going to go. It doesn't work anymore. So Newton's laws are not really totally 100% true. They're true in certain situations. That's fine. It's still a law. It's a set of observations. But it was disproven in some certain situations. And then the theory, the other side of that, atomic theory is the theory that all matter is made of atoms. Have you heard of that? Ever heard of atoms? We'll talk a little more specifically about what those are, but the idea that all matter is made up of these tiny, irreducible parts called atoms that give it its essential properties of whatever it is. If you take that as a theory, then you can predict all this stuff that happens, like metals have metallic type properties and so on and so forth. You can predict chemical reactions, but all of that has to start with the assumption that it's made up of atoms. And until recently, we couldn't see atoms. So that was a theory. That was the idea of what was happening kind of behind the scenes. How are these things happening? Why are these things happening? So those are kind of examples that atomic theory, we would not call that controversial, right? You know anybody who doesn't think stuff is made of atoms? Probably not. We're pretty sure about that one. But it's still a theory, not that it's not good enough, it's just because it explains something behind the what we see rather than simply describing a particular phenomenon. So you think you get that distinction? A really weird thing is going to happen. We just took, I don't know, 10 minutes describing these things in detail. And if I ask each one of you right now, what's a scientific law, what's a scientific theory, you probably all say the right, what we just said because we've just been talking about it. In a couple weeks, we're going to have a quiz. And then a few more weeks after that, we're going to have a test. And if something like this comes up on that quiz or that test, a bunch of people are going to get it wrong. Does that seem crazy based on what you just said? The reason for that is that these definitions, the wrong definitions that we talked about, are so deeply ingrained in us because that's what we've thought for so long, that you're actually going to revert to that wrong definition. A bunch of people are, without even knowing it, without even thinking about it. Suddenly, you're going to be totally sure that a law is like more true than a theory, and a theory is not as good or something like that. You're going to go back to that kind of a definition. So make a little star in your notes. Make a little reminder to yourself to come back and revisit this, even though it seems obvious. And right now, you're all thinking, "Okay, I got it. I thought I was wrong, but now I know the right answer, and I've got it." It's going to go back, and it's a totally weird thing, but it happens in these situations where we know something so deeply and so well. If we get information that contradicts what we already think we know, we throw it out, even if that new information is correct. So don't let that happen to you. Nobody's gonna let that happen to them, right? You're gonna be the one who gets it right. All right. Good.
So on your quiz, if you just say what's theory, whatever you have written there, that's enough for you. We don't have to go into that deep description of it.
That's enough for me.
Okay.
If you want to go and if you want to write a bunch about it and be more descriptive, that's fine.
But that's enough.
It's enough. Yeah. Yeah. The important part is that it's not what everybody thinks. That a scientific theory, a scientific law means something different. So let's make a couple little notes here just to be sure here. So a theory needs evidence to support it, and a law needs evidence to support it. And it can be contradicted by contrary evidence, by evidence to the contrary. So if enough evidence piles up opposing one of these things, then we no longer consider it to be correct. If something continues to support it, then we consider it to be more and more likely to be correct. Okay. So now let's talk a little bit about that certainty and that uncertainty. We'll leave that up there. One of the things that I love most about science and that attracts me to it so much is this idea of uncertainty and doubt. Has anybody thought about this with respect to science? Why is doubt important in science? Why is uncertainty important in science? If science is about getting things right, why is an uncertainty or a doubt important? What do you think?
It allows you to discover.
Yeah, it allows you to discover things. How was knowledge acquired before the scientific method? Before thinking about science in this way, the specific way that started, well, a lot of cultures did this, but a few hundred years ago or something, I'd say. How did we get knowledge like in, I don't know, Europe in the 1200s or something? How did somebody learn things? Anybody ever think about that?
I think by actually doing it, or asking themselves why, and then trying to see how they would come up with the answer, and see how they would make fire. And how do you make fire? You have to practice with two objects.
Right, but that's actually kind of a modern mindset. The idea that the truth is out there and we can just go find it out if we work at it. How did it work before that? Do you want to? Yeah.
Like, just depending on what you were told?
Yeah, that's it. Is all knowledge was authoritarian. Somebody told you what was right. Whoever was in charge got to make the rules and got to tell you what was true. If the king says that, you know, the earth is flat, then the earth is flat. And if the, you know, so it was kings, it was religious leaders, people like that. Whatever they said was the truth, that was the truth. And you just believed it, and that was fine. So science is really, it's revolutionary in the best sense of the term. It allowed people who were not in power, not that science doesn't have its own problems with power, but it allowed people who were not kings and were not leaders to say, you know what, I don't think that's right. I'm gonna go check it out for myself, see what evidence I can find, and then come to a new conclusion. And that's why early scientists kept getting killed, because they would contradict the leaders and say, well, you know, you think this, but actually I did all these experiments and it seems more likely that this is true. And then they'd, you know, get killed or whatever. So, so we don't really think about that anymore when we talk about science, but that doubt is still important. You know, you can be the most famous, most important scientist in the world, and somebody who's not famous and not important can find problems in your experiment, call you out on it, and you're wrong. If you can prove something through experiment, through observation, it doesn't matter what your position is. Now that's an idealized version. Obviously in the real world, we still have these kinds of power and authority issues. But that's what's, to me, kind of so magical about science, is that if a good scientist should always be open to doubt, should always be open to whatever you think is actually wrong. And so if somebody proves that you say, oh yeah, that's right, I was wrong. Good job. And then we move stuff forward in that way. So what is this, why is this important in our class? Are we going to be proving any great scientists wrong in this class? Maybe, right? Maybe. We might find out some good stuff. You don't know. We got to keep open to that possibility. But more concretely, why it's important, and the next thing we're going to talk about is in measurement. Who here has measured something before? Anything? For any reason? Most people. Tell me one thing that you measured. Anybody measure anything today? What did you measure today?
Floor plans.
Floor plans?
Yeah,
Okay, so you measured like a room or just the plan itself?
just like plans on the computer.
Okay, so that was like a length measurement. What kind of a tool did you use to measure it? The computer, okay, yeah.
Gum tissue?
Gum tissue. Like in a person's mouth, I would assume? Yeah. Okay, how do you measure that?
It's an instrument called a probe, and it has a little scale. It's
Yeah.
usually a depth.
Right. You don't want to get those fives.
No.
Yeah, so you measure the depth. Do you know what that is a measurement of? Like, is there a
It's
unit?
just a depth of how deep your gum is at recession. So they go by where it receives to the line of the where your gums are usually. They
So it's probably like millimeters.
millimeters.
Yeah.
It's like from 1 to 10.
Okay.
And healthy is 1 to 3.
Yeah. I remember having that done and being like yelling at me for having the fives. But I really like candy, so it's kind of, it happens. Yeah, so that's a good example. So this measurement, this probe measurement in millimeters. What else? Other kinds of measurement. Anybody else measure anything? Let's say in the last, I don't know, while. Did we measure anything this summer?
Cooking.
Cooking. What'd you measure the last time you cooked? Milk? In volume, like a cup or? Yeah. Okay, so that's a volume measurement. Okay. How did you make sure in each of those measurements that you talked about, or any other measurements that we didn't talk about, how did you make sure that that measurement was exactly right? You looked at it. So show me if you don't mind my probing into your cooking technique here. And I'm not going to judge you on this. We're just going to use this as an example. When you measure that cup of milk, first of all, what kind of a tool do you use? A cup, like a measuring cup. And does it have lines on it, or is it? Yeah. So when you pour the milk in, how do you know that the milk is exactly at the 1 cup line? Okay.
I poured it in, I looked at the line, see that it's at 2 cups.
Okay, so 2 cups, yeah. All right, and you tilted your head so you like go down to see it. Because what happens if the thing is up here and you just pour to the line? Based on looking at it like this, what would happen?
I'd probably go over.
Yeah, you'd be wrong because you got a different angle from this, right? Good. All right, there will be a point to this, by the way. So good, it sounds like, so what'd you make? Something good?
It's macaroni.
Oh, okay, sounds good. Nothing wrong with that. All right, so then let's go back to the gums. So you measure this tool, it's got little lines on it. How do you make the distinction which line that you're gonna call it? Like, does it ever fall in between lines?
It does, but when it falls in between, I think you just go to the higher number. It depends how
Okay.
the gums are, they look. So I think it just depends on practice and what the doctor says too.
Okay, so there's a judgment call there. And that's really important because actually in any measurement that we do ever, there is a judgment call. When you measure that 2 cups of milk, you might think it's right on that line, but someone else might say, it's a little above that line, right? Or a little below that line, or that line is thick itself. How do you know if it's on the bottom part of the line or the top part of the line? And like you just described with the gums, sometimes it's between that 4 and the 5, and somebody has to make that call. Is that a 4 or is it a 5? And maybe you have a rule like always round up, but like you said, sometimes you just have to look at it and kind of make that judgment call. And it's important when we work in the lab, when we do our measurements, that we have that same attitude, that we are measuring to the best capabilities of our instrument, but we are also making a judgment call. And let me show you what that looks like. So if I can find it. Here's a book, our book. I'm going to, what's going on here? Okay. I guess this thing doesn't have the thing that lets me select pictures in it. The computer upstairs does. Okay, well, we'll draw our own. That's fine. So I'm going to draw, actually, as long as we're drawing our own, I'm going to draw what we call a graduated cylinder. You're welcome to draw this with me or not, whatever you want to do. Has anybody ever seen an instrument called a graduated cylinder, a chemistry instrument? It's a long tube that we use to measure liquids in labs, and it has little lines on it, so you can. It's basically a measuring cup, but it's a tall cylinder, and we'll use that a lot in lab. So it looks like this. I'm just going to pick kind of a spot somewhere up on the graduated cylinder. Let's say at 4, and at 5, and 6, and then there's going to be a line right in the middle of those. And 4 lines like that. Now, obviously, it's not perfectly spaced, but you get the idea, right? When we measure liquid, we would fill this thing up to whatever we wanted to measure. And we need to write down a measurement. So our liquid measure might look something like this. If you've never done this before, the reason I drew it curved down like that is because when you fill up a cylinder like this with a liquid, especially something like water with a high surface tension, it makes that shape, kind of crawls up on the sides. Does anybody know where do we measure from? Do we measure from the side where it crawled up or kind of from the bottom?
On the bottom.
Yeah, we're going to measure from the lowest point on that curve always. So we have our graduated cylinder flat down, and we kneel down so we can get a great look at it. Maybe we put a piece of paper or something behind it so we can really see that level nicely. And we make a decision as to where that bottommost part is. So let's say it's, all right, this thing's not exactly calibrated right. There we go. All right, so let's say it's right there. So right, looks like based on my line, on that line. Did we just freak out about something? No, we're good. Okay. So right on that line, let's say. How are you going to write down this measurement? Well, we need to know something about how we write down measurements. We always write down all certain digits plus one uncertain digit. Now what does that mean? All certain digits plus one uncertain. This is this judgment call that we're talking about. And what that means is that a particular amount of the numbers that we write down, we're going to be super sure about. And then that very last one, we're going to make an estimate. All right? So I would say it is for sure between 5 and 6. Would you agree with me? That liquid level is definitely between 5 and 6. So that first digit is going to be certain. 5 point something. All right. Now, if we zoomed way in on this, let's do that so we can. Let's see if we zoom way in on this. There's 5, and there's just 2 ticks. We're so zoomed in, all we see is the 5 and the 2 ticks above it. And let's say that level comes right here. So we're so zoomed in here that this thing is going to look kind of like this, if it really, whatever. Anyway, focus on the red line. So the red line shows us exactly where it is between that 5 and that next tick. Because that line is surrounded by the 2 ticks, we can say that we are pretty sure, in fact certain, that that's between 5.0 and 5.1. You guys see that? It's for sure between those 2 ticks. So we know that it's less than 5.1. So our next digit is 0. We know that it can't be more than 5.1 because if it were, it would be above that next tick. And it's not. All right. That's all of our certain digits. How do we know that's all of our certain digits? Because there's no more ticks. There's no more little marks for us to compare it to. We're now in open water, in outer space, in between these 2 ticks, and there's nothing really to guide us to show us what the next digit past 0 should be. So the last one is uncertain. We guess. What's your guess? What would you call that? 9? Sure. Anybody disagree? I think 9 is fine. Maybe 8, maybe even 7, something like that. Yeah. So we might call this 5.09 milliliters. These 2 digits are certain. This one is uncertain. You see how that works? We're going to do some practice. You don't have to get it right now. But that might be different from how you've measured in the past, whether it's milk or whether it's measuring something with a ruler or whatever. We usually just kind of eyeball it and say, oh, it's about whatever. Have you ever wondered that to yourself though? Like, how do I know how many decimal places to write? Let's say this thing was exactly on the line. Is that 5? Is that 5.0? Is it 5.00? 5.000? Well, with this rule, you'll always know exactly how many decimal places to write, because it actually matters. Now, when we write down a scientific measurement of 5.09, we are saying that this number, whoops, sorry, I just wanted a different color here. We are saying that this number is between 5.08 and 5.10. Okay. So that uncertain digit is going to be plus or minus 1. Meaning if we call it 9, that means that we think that it's somewhere between 8 and 10. So we're going to have plus or minus 1 on that last digit, which means that our overall measurement has this range of being between 5.08 and 5.10. That's the number we've reported. So every number that we report is really a range. There's really some doubt and some uncertainty built in to that number. No matter how many decimal places out we use, it's always going to have this little bit of uncertainty based on that last digit. All right, so let's try it again. We're going to use the book's pictures now. I'm going to zoom in so you have to do it. Can you guys see that okay? Normally I would copy this over and put it in the notes, but this computer apparently doesn't have that feature. So we'll just do it like this for now. Take a look at this ruler. This is in centimeters, and we're being asked to measure the length of that stick. Now just use the top ruler, and let's go through that procedure again of figuring out what we're certain about and then what's a guess. So what are we certain about in terms of where that is? What do you know for sure? Yeah.
It's between 4 and 5.
It's between 4 and 5. So our number is going to be 4 point something. Everybody see that? It's for sure between 4 and 5. All right, do we get another certain digit? Do we know exactly what the next one should be? We don't. Why not? There's no ticks. There's no more little marks there. So we're out in space here. We don't know where exactly that one is. So what does that mean for our next digit? That's our uncertain digit. But for a correct measurement, we should also write that one down. So what would you call this measurement? Anybody?
4.4.
4.4. Sure. Everybody see that? Now, would it be wrong if you said 4.3? No, because that's the last estimated digit. Would it be wrong if you said 4.9? Yeah, that's probably a little far off. You need to do a little bit better estimating. Right? Now, again, that's going to depend a little bit on your tool. If those bars are so close together that you can't make that distinction, maybe some of you sitting in the back think 4.9 looks fine to me because I can't see that thing at all. That's maybe okay. Again, it's going to depend on your tool. But in general, that last digit we should be able to get within 0.1. Okay, now this one's going to be tough because this is as big as I can zoom in. But can you see that, the second one? So this is that same measurement, or it's supposed to look like the same measurement. But now we have a little different tool. Now our ruler has some extra lines on it. So what should our measurement be in this case? Anybody want to give it a try? Actually, let's change that. Everybody who can see this reasonably well, give it a try. See if you can write down a measurement of that wooden stick using this ruler, and then we'll see some we'll see what some of the answers are, or some of the measurements, some of your measurements are. Oops. Got some measurements? Maybe? Anybody still thinking about it? Okay. Anybody want to volunteer a measurement? What'd you get?
4.55.
4.55. Okay. Anybody get something different?
4.57.
Okay.
I said 4.58.
4.58. Okay. Anybody get something wildly different? 4.56. I wouldn't call that wildly different, but yeah.
Sorry.
That's okay. No, that's fine. Others? So you see the difference in those two measurements. It doesn't seem like a big deal, but let's think about what that really means. So yes, those are all correct. Those are all fine. Based on staring at the screen as closely as I can, this is page 28, by the way, if you have your book, but it looks like it's a little bit closer to the 6 tick. So I would probably call it 4.57 or 4.58, something like that. That's because I can see it a little bit differently. But let's look at the difference in those two measurements. So that first one we said was maybe like 4.4, I think somebody said, right? And that was centimeters. And then the second one we said was 4.57. Now, never mind for a minute that the second measurement is a little bit better in that, because it's more precise. Let's look at what it means to have that extra decimal place there. Remember that last digit gives us plus or minus 1 in our uncertainty. So this first measurement, what is the range of this first measurement? What is it between? If we write down 4.4, what are we saying is the range of the measurement? Yes, but more specifically, it's a little smaller range than that, because we know a little bit more than just between 4 and 5. If we write down 4.4, we're saying that is, yeah.
Between 4.3 and 4.5.
Right. So when we write down 4.4, we're really saying between 4.3 and 4.5 centimeters, which is 0.2 centimeters difference. 0.2 centimeters is 2 millimeters. We'll get into that, but 0.2 centimeters difference. So when we say 4.57, what are we really saying in terms of a range?
It's between 4.56 and 4.58.
Yeah. Which is 0.02 centimeters difference. So 10 times smaller. 0.02 centimeters versus 0.2 centimeters. And this is even more strikingly demonstrated. Let me write down a couple numbers for you. Here's where this comes up, or where this will come up in lab. Let's say one person writes down a number as 5 centimeters, and the other, just because they're being lazy and they don't know how many decimal places to write down, and the other person gives it a guess and says, well, you know, I'm pretty sure about it, so I'm going to say 5.00 centimeters. And maybe you've done this before, you know, measuring around the house or wherever, you measure something and you just kind of make a guess as to how many decimal places you're going to write down. You done that before? Maybe? Yeah. So let's see what that difference is. If somebody says 5 centimeters, they're really saying what in a scientific measurement? If you write down 5 centimeters, what are you really saying in terms of how big of a range your measurement is?
It's between 4 and 6.
Right. So we're saying if we only write down that one digit, we're saying that measurement is really between 4 and 6 centimeters. That's a big range. So you're saying it's somewhere in this 2 centimeter range, I don't know where, somewhere in there. And if we say 5.00, then we're saying it's between 4.99 and 5.01, which is a really, really tiny range. It's a much, much, much smaller range. And I guess what I want to impress upon you is that that's a really important difference, especially in a chemistry lab. When you take down those measurements, if you're off by a decimal place, it may not seem like much to you that 5 versus 5.00, it's like, well, isn't that the same? It's really not. Because of that uncertainty that's built in, not having those decimal places leads to a much lower precision. And similarly, if you put too many decimal places, then you're saying that your measurement is more precise than your tool actually allows it to be. But we are constrained by the tools we use. If we use this top ruler, the best we can do is 4.4 or 4.5, let's say. If we use this bottom ruler, we can say 4.56 or 4.57, and that's totally different. That's that's 10 times more precise of a measurement. What about C? How would you call that measurement in C? Yeah, that one would be 3.0. How'd you come up with that? That's right.
There's no marking, so I just guessed on 0 because it looks like it's right on the line.
Yeah, another way of saying that is we know the 3, we know one digit for sure. But that second digit is going to be an estimate. Like you said, it looks like it's right on the line. Doesn't mean it is exactly right on the line, but to us it looks like it's about on the line. So 3.0 is what we write down. We can't write down 3.00 for this because that would require an extra set of ticks that we don't have to look at. Okay. I think there's another one here. Now this is a spot where we're going to vary a little bit from the book. The book will talk about these things called significant figures. Has anybody learned that before in high school or anything? So there's rules about what you do when you do calculations with these measured numbers. for instance, if I put that 5.57 something in a calculation and you calculate it with some weird number and you end up with this huge number of decimal places, how do you know how many decimal places to keep? There's rules about that. It's called significant figures, and it's beyond what we do in this class. So we're not going to go into that. The book does go into that. So make sure that you skip those chapters and those problems on significant figures, because that's not something that we're going to deal with in this class. All right. It is important to measure things properly, but we're not going to worry about the significant figures in the math. Now, one thing where this gets a little bit weird sometimes is really big numbers or really small numbers. Right, so let's say we did all these examples in centimeters. What if that was millimeters? Same thing, right? You just do it the same way. What if it's nanometers, which is a few more down from there? Same thing. But what if we then wanted to express those in a larger quantity like meters? We might come out with some number like this. Whoa. Computer just kind of freaked out at me, sorry. Let's use some of our same numbers here. Let's say we came up with a number like that. 0.0000499. Tiny, tiny number. How do we deal with measurement uncertainty and stuff like that with these tiny numbers? The answer is the same. But when we try to report those numbers, it gets a little messy because of all these zeros, and you don't want to write that thing down a bunch of times, right? So what do we use as kind of a shorthand to deal with that? Anybody know? Yeah, is that what you're saying? Scientific notation. Everybody love scientific notation? No. All right, we're going to talk about it right now because it is important. In chemistry, whether we like it or not, we're going to deal with some really big numbers and some really small numbers. The reason is atoms are really, really, really small, and like measurable quantities of atoms, like a handful of them, is a really, really huge number. So we need to be able to deal with really small and really big numbers. We're going to do that through something called scientific notation. So here's how it works. Rather than writing 0.0000499, or let's look at another example. Let's look at a really big number. Okay. Rather than writing those ways, we're going to focus on the important part of the measurement, what we call the significant part of the measurement, the 4, the 9, and the 9. And the other stuff is all just placeholders to tell us how big or how small it is. So the way we do that is we move the decimal place over until there's just one significant digit to the left. For this one, it's going to look like this. Move, 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 move. Everybody see that? I moved it until there's just one of those significant digits to the left of that spot. And we count the number of times that we moved it. So that's 1, 2, 3, 4, 5. We're going to do the same thing over here. The decimal place right now is at the end, and we're going to move it to that same position right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So for the really big number, we're going to call that 4.99 times 10 to the, what did I say, 14? And the really small number is going to become 4.99 times 10 to the negative 14. Whoops, not 14, 5. Because we only moved that one 5 spots. So if it's a small number, less than 1, we're going to use a negative exponent. If it's a big number, we're going to use a positive exponent. And that's called scientific notation. There will be some practice from this in the book. That's the general idea. More important, probably to us, is dealing with scientific notation with our calculators. Does anybody have a calculator here that you plan on using in this class? No? Okay. You probably want to get one. we will be doing calculations. We will be doing calculator stuff. You don't need a super fancy thing. You don't need a graphing calculator. Any basic calculator or a scientific calculator would really be better. But we are going to need to do these types of calculations, so it'll be helpful to have that with you. Unfortunately, I can't let you use your phone as a calculator because you can look up other stuff on your phone. But so please pick up just a cheap calculator somewhere that you can use on quizzes and exams. But anyway, I guess since nobody has that, we will talk about how to do this on a calculator later. The tricky thing is because of that multiplication, you can't necessarily just punch it in the way that you think you want to. So most calculators have a special little key for scientific notation, and I want to show you how to use that. It makes all the calculations much easier in this class. And you'll always be allowed to use a calculator for everything, exams and that kind of stuff. So we'll do that. Okay, sound good so far? Okay. All right, we're going to get started a little bit on unit conversions and measurement conversions now, which I know is kind of a tough thing, and so we're going to spend some time on it, and we'll quit a little early today too. But we want to be able to answer these types of questions. So this is one, I think it's in the book somewhere, and we're not going to start right off with this, so I'm not going to write it down, but a patient needs 0.024 grams of a sulfa drug. How many 8 milligram tablets should be given? Those kinds of problems. Have you heard that sorts of things before? You're going to be like, oh no, this is going to be terrible. But these are important calculations, especially for going into the health professions. I don't know if you've noticed this, but a lot of medications, especially if you're working in a hospital, are measured in all kinds of different weird ways. Have you ever noticed that? Like some things are in milligrams, some are in units, some are in percentages, or there's different types of percentages. Have you ever looked at an IV bag? The different things in the IV bag are often actually given in different units, which we'll get into that a little bit later in the semester too. So not being afraid of that and being able to convert from one unit to another is really important. If you go to something like nursing school, they're going to really hammer you with that a lot. And so if you get it now, you'll be all set. You won't have to worry about it then. But that's one of the that's really a way. I mean, there's of course lots of ways that people in medical professions save lives, but if you can catch an error, like a conversion error on a drug, you could really save somebody's life. If there's a mistake with how much of a drug someone is given because somebody did a conversion wrong, that could be a big problem. You know, as you know, you don't want to take too much or too little of a drug. So being used to this, understanding, especially within the metric system, how to deal with these different types of units can be really, really important with your future career. So let's look at that. We're not going to go through all the metric prefixes as they are in the book. If we jump back to the Blackboard here for a minute, and you look at our measurements tab, you'll see in the chapter objectives that the prefixes that I want you to know for sure are kilo, centi, and milli. All right, there are others, and many of you probably know some of them, but we're going to focus on 3 of the most common: kilo, centi, and milli. So for those of you who don't have a lot of experience in the metric system, the way that this works is you have some base unit, like a meter, and then depending on which prefix you put in front of it, you're looking at a particular fraction or many of that meter. For example, a centimeter is how many meters? Careful. It's 100th, actually. There are 100 centimeters in a meter. Right? So 100 centimeters is 1 meter. How many millimeters are in a meter?
1,000.
1,000, right. And how many kilometers or kilometers are in a meter? Not quite. Yeah, it's actually 1,000th. So that means that we go the other way. 1 kilometer or kilometer is 1,000 meters. The neat thing about this, if you haven't used this a lot, is that this works for any kind of unit. So if we're measuring mass in grams, we can have 100 centigrams, which is 1 gram. We can have 1,000 milligrams in 1 gram. And then we can have 1,000 grams in a kilogram. You've probably seen that before. And that's going to be the same for liters, milliliters versus liters versus centiliters versus kiloliters. Anything, any kind of, you mentioned joules earlier, which is a measure of energy. You can put the same prefixes on there. So anytime you put one of these prefixes on that particular unit, whatever it is, and we're going to look at a lot of different units over the semester, that always holds true. There's 100 of centisomething in a something, there's 1,000 millisomething in a something, and there's 1,000 somethings in a kilo something. That's kind of an awkward way to put it, but that's how it works. All right, so if you remember those relationships, you'll always be good. What's another way, if you've had experience with this, what's another way that's nice to convert between units in this type of a system? Anybody ever worked with this? So let me give you an example. Eight grams, which we would write as 8G. How many milligrams is that? If I want to know 8 grams in milligrams, what do I do to do that conversion?
Multiply by 1,000.
You multiply by 1,000. So there's a couple ways we can think about doing that. One way that we're going to look at a lot is something called the factor label method. Is anybody familiar with that? What do you know about that? Oh, I just heard a groan. That's all right. What do you know about the factor label method?
Do like 8 grams over 1, and then you match it up diagonally.
Yeah, right. So what we're going to do with that is we're going to take our 8 grams and we're going to divide it by 1. The reason we do that is just to make it into a fraction. You can divide anything by 1, it's still the same thing. So we make this into this fraction. And then we multiply it by another fraction where the units are such that the one we want to get rid of is on the bottom, and the one we want to turn it into is on the top. So in this case, I asked you how many milligrams are in 8 grams, right? So that means our grams go on the bottom because we don't want those. And instead, we want milligrams. So those go on the top. The reason this works is that in math, we can say that these things cancel each other, which just is kind of a way of saying that it's a type of identity. And what that means is that we're left with milligrams. Now, we have to fill in the blank. And the blank is how many milligrams are in a gram. So how many milligrams are in a gram? 1,000. So we put that 1,000 here and the 1 there. So we know that there are 1,000 milligrams in 1 gram. And now our math problem is set up for us, and our answer to this expression is going to be however many milligrams are in that many grams, exactly what we wanted to know. To do this calculation, you take out your calculator if needed, and you multiply by everything along the top, and you divide by everything along the bottom. And when you do that, you'll get the answer. Now notice I wrote down the units before I wrote down the numbers. That's an important part of this technique. What it means is that we're going to track the units. We're going to follow the units through, and we'll put the numbers in later. And that's going to help us make sure that we're always getting things on the right side in terms of tops or bottoms. So if we evaluate this expression, what do we get? In other words, if we do this math through, what's the answer? Can anybody do that without a calculator? 8,000. So that means that our answer for how many milligrams are in 8 grams is going to be 8,000 milligrams. All right. And the neat thing about this technique, that was a pretty basic example, but this works for all kinds of complicated stuff. So let's go back to that problem that I mentioned at the beginning and everybody kind of went, ugh. And let's see how we can use this to come up with the answer to that. I'm going to write out this problem for you. A patient needs 0.024 grams of a sulfa drug. Anybody know what a sulfa drug is? What? Not quite. Well, I guess it can be. Yeah, it's a type of antibiotic, generally. Yeah. It's mostly these days used topically because a lot of people have allergies to it, and so you don't want to get too much in your system. But things like topical antibiotics, and they're useful in, I want to say urinary tract infections is the only place they're still widely prescribed. I'm not sure if that's true. What? Is that sulfa? Okay. That's not a sulfa drug. That's a, okay, yeah. Ciprofloxacin is a fluoroquinolone antibiotic, I believe, right? Anybody know? Antibiotic classes, okay. We can look it up, but I think that's right. So a patient needs 0.024 of a sulfa drug. How many eight milligram tablets should be given? All right. So the prescription is written, give 0.024 grams drug. You look in the stuff and there are 8 milligram tablets. So you got to figure out how many 8 milligram tablets to give to add up to 0.024 grams total. Now, some of you might be able to look at those numbers and just kind of do it in your head, and that's great. But we're going to go through it as a factor label conversion type problem so that we see how we could do it in that way. So the way I would think about this is how many 8 milligram tablets are in 0.024 grams, or the other way of thinking it is how many tablets in 0.024 grams. That's really the question, how we want to frame it. How many tablets in this certain number of grams? We have our unit of grams. We have 0.024 in grams. We want to turn that into a unit of tablets. So let's set that up. All right, so we take our initial number, we'll put it over 1. The only reason we put it over 1 is sometimes that initial number is a fraction. And so if that were the case, we wouldn't put it over 1. But since it's just a number, we're going to pretend it's a fraction and put it over 1. So that's how many grams we need. And we want tablets. But we don't know how many grams are in a tablet. We know how many milligrams are in a tablet, right? You see that? So that means we're going to need an intermediate step. Sometimes what's helpful in these types of problems is to set up a plan of how you can get from one unit to another. In this case, we can't go directly from grams to tablets. So instead, we have to go grams to milligrams to tablets, because we do know how many milligrams are in a tablet, 8 milligrams in a tablet. So here's how that would set up. We take our grams over here, and then we're going to turn grams into milligrams. So gram goes on the bottom, milligram goes on the top. That's going to allow the gram to cancel, and we're left with milligrams. But we don't want milligrams, we want tablets. So we're going to also cancel milligrams and turn it into tablets. So that's our plan. That's how the units look in these types of an expression. Now we have to fill in our numbers so we actually have something to calculate. So we're going to look at each of those fractions and decide how many of one thing are in the other. So between milligrams and grams, how many milligrams are in a gram or how many grams are in a milligram? What do you think? 1,000 milligrams in a gram. Okay, so we'll go 1,000 milligrams per gram. Okay, how many tablets in a milligram, or how many milligrams in a tablet? 8 milligrams in a tablet. We know that from our problem. That's not always the case in every tablet, but for these particular tablets, that's how it works. So we've got 8 milligrams in each tablet. So now we have a problem that gets us from grams to tablets. To do this calculation, we would multiply by everything in the top, divide by everything on the bottom, and that should give us our answer. So 0.024 times 1,000, and then divided by 8. If you have a calculator, you can do it. We'll just pretend. Okay, everybody got your answer? Yeah, so you come out with 3. Good. Now there are other ways to do this. You may have your own shortcuts. You might have done that in your head. You might move decimal places over back and forth. This is the kind of thing that you just need to practice. If you haven't done this before, it just takes practice. You do a bunch of problems like this, and suddenly it seems obvious. Now it doesn't mean they don't get trickier, they don't get harder. Certainly we're going to throw in a couple of things next. But if this just seems crazy to you, like you're never going to be able to do this, I would encourage you to start with these, look in the book, and start practicing. The book, at end of chapter 2, has a bunch of problems like this. And if you can work your way through them, either by yourself or with a tutor or with me, you'll definitely be able to get this. So I realize it's going a little quick now for some of you, but I think you can get it. All right. So let's throw the last kind of twist in here. What happens when we're not in the metric system anymore? So what happens? What's different about this type of a method when we're not dealing with the metric system?
Everything's not like in factors of 10.
Yeah, that's the only difference. The technique is actually the exact same. The only difference is the numbers get a little bit messier. So we're not going to have 1,000 and 100. We're going to have whatever weird numbers. But the technique is exactly the same. So let me show you what that looks like. Oops. Right. How many gallons are in 75,000 milliliters of water? So going from the small scale, milligrams, up to a rather large scale. How many gallons are in 75,000 milliliters of water? What is this measurement gallons? Anybody know? How many gallons are in a milliliter? How many milliliters are in a gallon? Does anybody know? I don't know. No, because those are different systems. We call gallons part of the English system or the imperial system, and milliliters are the metric system. So we need some more information to do this problem. And whenever you get a problem like this, you'll be given more information to use. So in this case, I'll give you a couple pieces of information. 1 quart is 946 milliliters. And how many quarts are in a gallon? 4, yeah. And there are 4 quarts in 1 gallon. Okay. So we don't have a direct conversion between milliliters and gallons. But we do have milliliters to quarts and quarts to gallons. So what's going to be our plan in terms of units and how we're going to get from milliliters to gallons? We want to just, what would you do? If we start with milliliters, where do we go from milliliters? We'd go to quarts because we have an equivalence. We have a factor that tells us how many milliliters are in a quart. So then where do we go from quarts? To gallons. So then we got it. So we set up our plan and we got it. Now you won't ever need to remember these kinds of weird numbers like 946 milliliters in a quart. You'll be given those numbers. But you do need to know how to use them. So let's set that up. We said that the plan was going to be milliliters to quarts to gallons. So see if you can set up the whole problem. And if you've got a calculator, go ahead and calculate it out, or if you've got a phone or something. And then we'll do it together. All right, so I know it's the first day everybody's scared, but would anybody perhaps like to come up and show us how you worked it out? You don't have to be scared. It's a nice group. It's non-judgmental. Also, it doesn't have to be right. Just you want to give it a try? Give it a try? Thanks.
You want me to just say it or?
Yeah, just write it on the screen here.
And then I
Okay.
used a calculator.
Okay, I think I got it. What do you think about that? Thank you very much.
Sure.
Similar to what you got? Got some head nods? Maybe? Yeah. All right, well, let's check it through the units. And the nice thing about doing this is you can always check it by looking at those units and seeing if they're going to cancel the right way. So if we want to get from milliliters to gallons, then we better cancel everything else and just end up with gallons. So does this milliliter here on the left have a pair on the bottom? It does, right? So this one can cancel with this one. And then the quart up here can cancel with the quart down there. So that leaves us with gallons. Then we check our numbers, make sure they're in the right place. And we see that they are based on what we were given up there. So this is probably right. So we calculate it all out. And I think I did this one. And I got 19.8 gallons. Did anybody calculate it out? Something similar? Is that what you got? Great. Okay. So when you calculated this out, you probably got a bunch of decimal places, right? So how did I decide 19.8? Like I said, we're not going to get into all those rules, so we just decide. I think a good rule of thumb to use is whatever is approximately the number of digits that we see in the problem, we'll use the same number in the answer. So like 946 gives us 3 digits, so I stuck with 3 in the answer. Again, if you're not satisfied with that answer, that's totally fine. If you want to come to my office, I will show you how to do it, or you can look at the book. It's not that hard. It's just not something we're going to do in this class. So we're just going to throw out however many decimal places we want. All right, great. So the good news is it doesn't really get any harder than this. All that we can really do is put in more terms. I mean, the class might get a little harder, but this particular technique doesn't get any harder than this. We can put in more terms. You know, maybe instead of milliliters to gallons, it's milliliters to, I don't even know, what's the next bigger thing than gallons? Barrels? Does anybody know? Like, what's the next unit up from gallons in the English system? Bushels? I don't know. So it's a bad example. But anyway, we could keep going to other stuff, and we would keep using the same technique. And when we get into talking about density next time, we're going to use the same technique to calculate around density, but we're going to have a number on top and on the bottom. But I don't want you to freak out about it because it's really the same technique. And all those unit conversions we do for the whole rest of the semester, whether it's metric system, English system, whether it's talking about energy or talking about volume or talking about mass or talking about moles, it's always going to be the same thing. So practice this in the book in the end of chapter 2, and you'll be in really good shape for when we do this throughout the whole rest of the semester. All right? So we're going to stop there. We're not usually going to end early, but we will today because it's the first day, and you know, got to get into things a little slowly, right? So please make sure you print out the labs from Wednesday. If you have any trouble getting into Blackboard, let me know as soon as possible so I can get you in. And we will do some fun lab on Wednesday with measurements and talk about safety and get going with the semester. So welcome. It was great to meet you all, and I'll see you Wednesday.